All right, recording. Section 10.2a, testing the difference between two population means, right? So prior to this, we were doing the looking at the difference between two population proportions, right? We did confidence interval and testing. Now we're going to do the same thing for population means, right? So last year, East Kentwood High School had 30 students take the AP Statistics exam. We were informed later that the College Board gave two forms of the exam which were randomly assigned to the students. Here are the results, right? So for Form A, there are 15 scores here, I believe, 3, 3, 3, 3, 4 threes, 4 fours, and 1, 2, 3, 4, 5, 6, 7 fives, right? Form B, distribution's a little bit different. 2 twos, 2 threes, 5 fours, and 6 fives, right? So if we kind of summarize the data on both of these, we would get a mean score of 4.2 for Form A and a mean score of 4.0 for Form B, which might suggest that what? That maybe Form B is a little bit more difficult. Might suggest. But the question is, does that just happen by chance, right? So what would be the difference of the means in the two samples? 4.2 minus 4.0 would give us a 0.2, which again, kind of the positive 0.2 means that Form A would be a little bit easier. Right? Scores were a little bit higher. So how could we test this? We could run a simulation and create sample differences and see if there is if we run into a similar result, right? So the best way to do this would be if we had enough students, 30 people, to what the assumption would be, that is, if a person scored a 3 on Form A, they would also score a 3 on Form B, right? So that would be the assumption, that Form A and Form B are equally as difficult, and somebody who scores a 3 on one should score a 3 on the other, right? With that in mind, we could take these 30 scores, right? Give them to 30 people, and then run a simulation where we randomly assign 15 to what we call Form A and 15 to what we call Form B, right? And then we could take the differences in between pairs of 15, right? And so as an example, or I'm sorry, not the differences, my bad, the sample mean from each one, from Form A, and then the sample mean from Form B. So let's say we took those 30 people, they got scores, and we gave assigned 15 of them to Form A, 15 of them to Form B, and we got the samples from each one, right? So again, just like we did here, we got 4.2 and 4.0. The next time we run it, well, we could get 3.9 and 4.1, in which case we would get a negative 0.3, right? No, 0.2, my bad. And we do that over and over again, right? We get the sample mean from each form every time we run it, and then to run it again, we reassign people to each form, 15 in each group, and then get the sample mean again. But again, that's under the assumption that a person who scores a 5 would get a 5, whether it's Form A or Form B. Okay. So here's the deal. We don't have the people to simulate that. So what I do have here is a website that has a simulation built in, right? So I typed in the data that we had there, right here, right? The same outcomes from Form A and Form B. And then using this simulation, I hit begin analysis, and what it does is it plots the data for us. It shows a bunch of test scores for test 1, a bunch of 3s, 4s, and 5s, and then for group 2, it shows 2s, 3s, 4s, and 5s. And then what we can do is down below, it's a nice little tool here. There's a drop down for doing a 2-sample t-interval, a 2-sample t-test, or simulate the difference in two means. And that's what we're trying to do here, is just simulate the difference. So the directions on this says, or the explanation says, it simulates the distribution of the difference in sample means when the observations are combined, shuffled, and redistributed into two groups. So it's exactly what we were talking about, right? We took all 30 scores, shuffled them up, and we randomly assigned 15 to form A, 15 to form B. So this is doing the same thing for us. We can choose whatever the number of samples we want to take. Doesn't matter. I'm just going to say 30 for right now. Okay. I'm going to hit perform simulation, and it's going to perform the actual. Let me hit clear here real quick. And I wanted to see adjust route. Okay, it doesn't give us that. I'm just going to hit the simulation here. Down below, it says count the number of dots, and I can choose greater than or less than, greater than, less than, or equal to. The number that we are looking for is 0.2, right? Back to our original question, 0.2. And count how many dots there are, okay? So in our case, we are trying to find if getting a solution of 0.2 or greater is kind of a common thing. Is it rare that it happens, or is it not? So we hit count, right? And according to this simulation, it says there are 10 dots in that specified region. And what I'm going to do here is, just for our notes purposes, to make this quick, I'm going to say edit, copy, and let's see, edit, paste. And we just, bam, just like that, we were able to insert that simulation. Okay. Hopefully that's legible. Right? So what we're able to find here is that there are, starting at 0.2, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dots, just like it said on the last page. 10 dots out of the 30 samples taken, 10 out of 30, that are a value of 0.2 or greater. So we get 1/3 or 0.33. Right? So when 3 says down here, East Kentwood had a difference of mean scores of 4.2 minus 4.0 at 0.2. Is this outcome surprising if we assume both forms are the same difficulty? Well, that's the simulation we just ran. We assumed that both forms were the same, and for that reason we were able to shuffle up all 30 scores and distribute them into two different groups, right? If we didn't have that assumption that they were the same difficulty, we wouldn't be able to do the simulation this way. But in doing so, and taking 30 samples and taking the sample means from each one, we can say that no, assuming both forms are the same difficulty, there is about a 0.33 probability of getting a difference of sample means of 0.2 or greater purely by chance. So it's the same type of thing we've done over and over again, right? Run this simulation, find out what's the probability of getting a value as extreme or more extreme than the one that we found in a sample. You know, we're testing to see if this is, did this just happen by chance, or or is this kind of a common thing? So, based on the simulation, do we have convincing evidence that one form of the exam is harder? And we can say no. Getting a difference of 0.2 or greater is not uncommon. So in this case, more than 5%, way more than 5%. We got like 33%. So we do not have convincing evidence. Right? Doesn't happen by chance. I'm sorry, there is a great probability of getting of that happening by chance, right? 33% probability. So it's not a rare occurrence. So this just kind of follows suits with everything we've been doing, right? So what are the important ideas here? Shape, center, and spread of a sampling distribution of x bar 1 minus x bar 2. Maybe I should clean that up a little bit. So the difference in sample means. So shape. Both samples must meet a normal, our normality, right? One, is the population normal? If it is not, is the sample size greater than or equal to 30? If it's not greater than or equal to 30, if we plot some sort of sampling distribution, is there any strong skewness or outliers? Okay, so it has to pass some of, one of these at least. And if it does, we can say it's normal. Center, okay, center of the sampling distribution for the difference in samples is equal to population mean for population, the mean for population 1 minus the mean for population 2. And then spread, in this case, is the square root of population 1 variance divided by N1 plus population 2 variance divided by N2. Right? And this is that whole, in order to get the new standard deviation, we are adding the standard deviations from both populations. Okay? All right, so checking your understanding. Let's give it a trial run here. Getting just the basics for today. So tonight's homework is just going to be about shape, center, and spread, right? How tall? The heights of young men follow a normal distribution with a mean of 69.3 inches, a standard deviation of 2.8 inches. The heights of young women follow a normal distribution as well, with a mean of 64.5 inches and a standard deviation of 2.5. Suppose we select independent simple random samples of 16 young men and 9 young women and calculate the sample mean heights of x bar m and x bar w. Okay? So a couple of important things here. We know that the population is normally distributed for both of these, right? So that helps us meet this requirement of normality coming from the population being normal. If population wasn't normal, then we'd have to start looking at sample size and some sampling distributions. We know that, we also know that the population mean and population standard deviations are 69.3 and 2.8 for men and 64.5 and 2.5 for women. It's one of those rare cases where we actually know the population standard deviations, right? Normally we don't have that. So what is the shape of the sampling distribution of x bar x bar for males minus x bar for females, and why? Well, we just set it up here, right? So since the population is normal for both populations, we can then assume that the sampling distribution for the difference between the two populations is also going to be normal, right? And it's going to have a center. We'll talk about that in a second. So approximately normal, because both of the men and women populations are approximately normal. B, find the mean of the sampling distribution. What do we say up here, right? This is according to what we learned about sampling distribution. So the mean of the sampling distribution for x bar 1 minus x bar 2, or in this case, x bar m minus x bar w, is equal to the population mean for one population minus the population mean for the other population. So in our case, 69.3 minus 64.5 gives us a mean difference of 4.8. Pretty simple. All right. And then lastly, calculate and interpret the standard deviation of the sampling distribution for sample mean for men minus the sample mean for women, or the difference in the sample means. Also straightforward, right? Finding the standard deviation by adding the variance is taking the square root. So in this case, we get 1.088. And it says to interpret, right? So we can say the difference in means typically varies by 1.088 from the true mean difference of 4.8.